Hello, welcome to our third video on proof by induction. Today we're specifically looking at how proof by induction can be used to prove the divisibility of something. The sort of structure that would look like in a question would be, let's say you've got a function of n and you want to prove that it's divisible by a particular number d for all the values of n that are integers within a particular interval that you can plug into your function. So, with that said, what is the structure? Well, it's the same rough structure that we're used to seeing for proof by induction by now. The first step is the basis case, which is to say that if we're trying to prove that f of n is divisible by d, we've got to show that it's true for n equals 1. However, it's worth pointing out in the last video, n equals 1 is 99% of the time the basis case, but you do have to adapt. If your basis case is going to be something different, it all depends on what the interval you're trying to prove your statement for. Normally, we are trying to prove the statement is true for all integers n is greater or equal to 1. That's why n equals 1 is the basis case. But if you were trying to prove something was true for n is greater or equal to 4, then n equals 4 would become your basis case. So do be adaptable. The second step is to assume the statement is true for n equals k. So we're going to assume that f of n is divisible by d for our particular mystery integer n equals k. And unsurprisingly, the third case that we have to deal with is looking at the situation where n equals k plus 1. We're having to show that if the statement is true for n equals k, then subsequently it must be true for n equals k plus 1, using that fact to help us. This is where things do get a bit different though, because for divisibility, it's a slightly different structure to how we were splitting things up before. It's also worth pointing out that there are multiple different methods for approaching this stuff, and actually if you look in the mark schemes for exam questions, they will often show all three of these different methods, so they're all valid. I'm going to be showing you one particular method because this is the particular way I like approaching these questions. If your teacher's shown you a slightly different method to this, I'm sure it's probably valid. It's probably one of the other of the three methods that the exam often accepts. And if you've been using that method and it works for you, continue using that method. I'm not here today to change what you do already if what you do already works. However, equally, if that method doesn't work for you, hopefully my method might work slightly better for you. So there we go. And if this stuff is new for you, as I said, this is my way of doing it. You might see some alternative ways of doing it if you look at other resources. But anyway, therefore the method we're going to use today is we're going to start off by looking at f of k plus 1, and then what we're going to try to do is we're going to try to split it up so that it's written in terms of f of k. But unlike the other situations we've had with proof by induction where you're writing it as f of k plus something or f of k times by something, we are going to have a slightly different structure because we're instead going to have a multiple of f of k then plus some other stuff as well. So it's kind of like a combination of two scenarios that we've had before now. So this looks quite complicated as a structure, and you see that there is that constant a. We're basically going to have a multiple, a numerical multiple of f of k. So that's what we're looking for. But what multiple are we going to choose? Well, basically what you've got to do is you've got to choose the value of a, choose the multiple of f of k you're going to have, so that the remainder we've got added on the end is a nice simple thing, or the most simple thing we can possibly make it. What does that mean though? Well, let me do an example to illustrate exactly what I mean there. Let's say I have something fairly straightforward like f of k equals a plus b, and let's say for whatever reason fk plus 1 was, let's say, 3a plus 7b. Now, we could choose lots of different multiples of f of k, but we want to choose a multiple of f of k. That means whatever we got to add on as the remainder is something that's really nice and straightforward. So therefore, we might want to choose to deal with all of the a's or deal with all of the b's when we're choosing our multiple of f of k. For instance, I could choose to have 3 lots of f of k, because if I do that, I'll have 3 lots of a, which means all the a's will already be accounted for, and then the remainder function will just be whatever's left over needed to deal with the b's. So therefore, as I've chosen 3 lots of a plus b, that means we've got 3 b's, so that means I need an extra 4 b's. So therefore our remainder was just in terms of b, so it wasn't too bad. So we've got 3 lots of f of k plus 4b in this scenario. However, there are alternatives. Why did I have to choose a multiple of f of k that just dealt with all the a's. So instead I wanted to focus on dealing with all the b's instead. Well, you are allowed to do that as well. So there is often more than one way of doing these questions. So instead what you would have done is gone, okay, I want 7b, so therefore I've got to have 7 lots of a plus b if I want to have dealt with all the b's. And therefore, though, that means this time we've got too many a's because I've got 7a and I only want 3a in f of k plus 1. So therefore, I've got to subtract 4a so that I've still got overall 3a plus 7b that we had in the original statement for f of k plus 1. So therefore, that would alternatively be, therefore, 7 lots of f of k minus 4a. So there you go. Those are the sort of things we're looking for when we're trying to split f of k plus 1 up. And then once you've done the f of k plus 1 stage, the final stage you'll have to do is, as always for proof by induction, the conclusion. That's the bit that doesn't really change at all. You just got to remember the wording and actually remember to write it out. There you go. Let's take a look at an example to actually put this properly into practice altogether. So we've got our function 7 to the power of 2n minus 4 to the power of n plus 1, and we're trying to prove that it's divisible by 3 for n is an element of the positive integers. So in other words, it's saying n is greater or equal to 1. A reminder of that notation, that's what it means if they do decide to use that notation. So starting off, we need to do the basis case. However, to make the notation a bit easier, I'm going to start by saying let f of n equal 7 to the power of 2n minus 4 to the power of n plus 1. If they haven't done that, it's a good idea to do this because it means it's easier to write out certain steps later on. So therefore, I'm going to say f of 1 will therefore equal 7 to the power of 2 minus 4 to the power of 2. That's 49 take away 16, which is 33. 33 is equal to 3 times 11. Therefore, it's divisible by 3, as we wanted. Hooray! So there we go. We've done the basis case. And that's that bit done. I haven't labelled it as the basis case, but, I mean, let's do that there. Basis case, there we go. Making it nice and clear, making it easy for the examiner to give me all the marks. The next step is we're going to assume f of k is divisible by 3. And this is where writing out the f of n bit is helpful because now I'm not having to write out that whole equation every time I'm referring to it. But now we've done that, now we've got to move on to the induction step. So therefore we've got to look at this statement for n equals k plus 1. So of course that's just our statement with k plus 1 plugged into it. So that would be 7 to the power of 2 lots of k plus 1 minus 4 to the power of k plus 1 plus 1. And then, therefore, you could do some algebra rewriting. That means we're going to end up with 7 to the power of 2k plus 2. And I could combine the k plus 1 to get k plus 2 in the power of the second thing. But I'm actually going to leave it as k plus 1 for reasons that will become clear very soon. Because what we're trying to now do after this is rewrite f of k plus 1 in terms of f of k. A reminder that f of k would just be, of course, our statement with n replaced with k. So, even though that should be fairly clear, I'm writing it up here for our own reference. And the problem is, although we've got the correct bases of 7 and 4, the powers are completely wrong with comparison to what we've got in f of k. So, therefore, what we're going to try and do is we're going to try and rewrite what we've got for f of k plus 1 by splitting up what's there using index laws, because we like the fact we've got a 7 to the power of 2k, but we don't like that power of plus 2 also included. So, therefore, using index laws, we can rewrite this as 7 to the power of 2 times by 7 to the power of 2k, because then that separates out that power of plus 2 that we didn't want. And then similarly, because we do want 4 to the power of k plus 1, that's why I left the k plus 1 as a separate thing, it's that extra plus 1 on top of that we don't want, so I'm going to separate that out as 4 to the power of 1 times by 4 to the power of k plus 1, because, yes, as a reminder, by index laws, if you multiply these things together, you add the powers together. So that means we've got 49 lots of 7 to the power of 2k minus 4 lots of 4 to the power of k plus 1. So that's what we've got so far. Now what we're going to try and do is we're going to try and rewrite this in terms of f of k, and that's where we're linking back to what we said a couple of slides ago, where we're talking about the fact we've got things that are multiples of what appears in f of k, and what you want to do is choose a multiple of f of k to separate out from this, so that the bit we've got left over, the bit that's added on at the end, the remainder if you will, is something that's as simple and small as possible. So one way of doing that very simply would be to just go, okay, I know we're going to need 49 lots of f of k, because that would then fully deal with the 49 lots of 7 to the power of 2k that I currently have in the step before. But then we know that we're going to have some extra stuff beyond that. So some of you might be able to just look at this stuff and work it out for yourself by realizing, okay, by writing this bracket as I currently have, we've got 49, or rather I should say minus 49 lots of 4 to the power of k plus 1, but I want minus 4 lots of 4 to the power of k plus 1. So if you're feeling confident, some of you might just be able to realize that means we need an extra 45 lots of 4 to the power of k plus 1, because then that will mean we have in total minus 4 lots of 4 to the power of k plus 1. However, some of you might not be entirely happy with just jumping to that, so you're welcome to do this extra stage here to help know that that's an extra plus 45 added onto the end. So the way I can work that out is I realize we've got the 49 lots of 7 to the power of 2k. I know I'm going to want to subtract 49 lots of 4 to the power of k plus 1, so that I've got 49 lots of both things. So I've got 49 lots of f of k. I'm trying to match the amount of both of those bases in both places. But therefore, what have I got left over? Well, what I'd have left over is I'd have minus 4 minus 49 lots of 4 to the power of k plus 1. And that is what then lets you know, okay, I've got 45 lots of 4 to the k plus 1 as the remainder, because minus 4 minus 49 is going to be positive 45. That means we can then rewrite what we've got as 49 lots of f of k plus 45 lots of 4 to the power of k plus 1. And that's great news, because we've now rewritten f of k plus 1 in terms of f of k, which is good news because f of k is something by the assumption stage we already know to be divisible by 3. But we've got this second bit, the remainder, that's still there, and we could do something to that to rewrite that to make that a bit more clear that it's also divisible by 3, because of course 45 is just 3 times by 15. So therefore we have 49 lots of f of k plus 3 lots of 15 lots of 4 to the power of k plus 1. Because 3 times 15 is 45. And so therefore we've now rewritten f of k plus 1 in a way that makes it super clear that it must have an overall factor of 3 for the entire expression. And that's good news because it means the expression must be divisible by 3. That's actually why, in my opinion, this particular method is my personal favourite, because I think it's the best, because most of the legwork is done by the algebra. It makes it pretty clear by the time you get to the end why the thing must be divisible by 3, and therefore you have to do less explaining to justify why the thing is divisible by 3, because the algebra speaks for itself. And that means you can therefore just launch straight into doing the usual traditional proof by induction conclusion that we always do, rather than having to add extra words to justify what was going on. So therefore, in solidarity with you, just like the other videos, I'm actually going to write the conclusion out by hand, because you're going to have to write it out by hand every time you do these questions. So to be a good role model, I'm going to do it too, rather than cheating and just having it pre-typed up. So therefore, we can say we have shown that if the statement is true, for n equals k, it must subsequently be true for n equals k plus 1. So that's the first bit you need to take off, showing that if it's true for n equals k, it must then be true for n equals k plus 1. And then, as we have also shown that it is true for n equals 1 by the process of mathematical induction, we have shown that it is true for all integers n is greater or equal to 1. There you go, that is the conclusion for proof by induction. However, there is just one more thing I'd like to show you in this video, and that's because 99% of the time the method I showed you just now will work as long as you choose a good multiple of f of k to separate out. It will mean the remainder part that's left over will also then factorize nicely to show that the thing that you're trying to show is divisible by is a part of that thing. But occasionally, just 1% of the time, no matter what you choose your multiple for f of k as, no matter what you do, it's not your fault. The remainder part that you've got left over will not factorize nicely instantly. You might have to do a bit more work. Well, what do I mean? Let's say we're looking at this example here where f of k, which is a mystery expression, is divisible by 6. The expression itself doesn't really matter. What I want to point out is you could get to a point where you've got something that looks like, I don't know, this. Let's say we've already factored out a multiple of f of k, but then we end up with something like this on the end. Now the problem is you can see just directly at our remainder part, it's not really entirely clear that is instantly divisible by 6 just because the number out the front is just a 2. And so therefore that's just showing it's divisible by 2, not divisible by anything more complicated than that. So therefore sometimes you have to do a bit of an extra stage by factorizing an extra factor out of the thing that's got the powers. So for instance, it's quite clear that 3 to the power of k plus 5 is just 3 multiplied by itself multiple times, and therefore you can factorize 3 out of that expression as well, because it's going to be 2 lots of 3 lots of 3 to the power of k plus 4 by index laws. And that's helpful because it means now we're able to rewrite it in a way that makes it more clear that 6 is a factor of that expression on the end. So just to make you aware that sometimes you have to do that little extra stage, that little bit extra manipulation to get what you're trying to show to end up appearing. So it's a bit mean when that does occur, but when you know the trick, it's not too bad. You know what you're looking for. Okay, that will do us for today's video. That's how you do proof by induction for divisibility. It's the one that a lot of students find the most difficult, but if you remember the tricks I told you in today's video, it's really not too bad. So with that said, I'll see you in a future video. Goodbye.